Imagine you're running a study to determine which of 3 competing diets produces the greatest absolute weight loss. You have a spreadsheet full of participant data, and you need to mathematically prove which regimen is the clear winner. Standard t-tests are risky here because error rates compound with every additional comparison. If we had 4 groups to compare, we would need to run 6 separate tests. Multiplying the 95% confidence level of each test together reveals an overall probability of only 73.5% that we've avoided a false positive. This is known as family-wise error. To evaluate 3 or more groups simultaneously without inflating that error rate, we use a one-way analysis of variance, or ANOVA. Mastering the ANOVA ensures the statistical integrity of your work. It prevents you from publishing findings that could later be debunked as simple mathematical artifacts. Start by loading the diets.csv dataset into JASP. Then navigate and select the ANOVA module. In the configuration window, you must map your variables correctly. Your continuous measurement, weight loss, goes into the dependent variable box. Your categorical grouping variable, diet, goes into the fixed factors box. Under the additional options, select omega squared as your effect size. While eta squared is common, omega squared provides a more accurate, unbiased measure of population variance, which is particularly important for smaller sample sizes. Before looking at your results, open the Assumptions Checks menu and enable every available option. These initial settings determine whether your final results are actually credible. Configuring them properly ensures your computational outputs are grounded in sound methodology. Stop before you read the main ANOVA table. Interpreting those results is scientifically invalid until the data passes its mandatory diagnostic checks. First, check the QQ plot to evaluate the normality assumption. We're looking for the data points to closely follow the diagonal red line. In this dataset, the points hug the line, confirming the data is normally distributed. Next, check Levine's test for the homogeneity of variance assumption. For the ANOVA to be reliable, we need a non-significant p-value here. Our result is above 0.05, meaning the variances between our diet groups are statistically equal. If your data fails this test, you cannot use a standard ANOVA. You would instead need to report the Brown-Forsyth correction, or consider the non-parametric Kruskal-Wallis test. Passing these diagnostics means the raw data is validated. The upcoming ANOVA results are now bulletproof. Now we can return to the primary ANOVA table at the top of the output pane. Look at the p-value for the F statistic. A value under 0.05 confirms that a significant difference exists among the 3 diets. With our omega squared at 0.214, we also know this is a large effect size. However, the ANOVA is an Omnibus test. It acts as a global alarm, telling us that a difference exists somewhere in the data, but it does not tell us which specific diets vary from each other. Remember the rule. If this Omnibus p-value is greater than 0.05, the investigation is over. You cannot perform further testing on an insignificant result. Since our result is significant, we have passed beyond the BIS gate. We now have the authorization to investigate exactly where those specific differences lie. To find those specific differences, expand the Post Hoc Tests menu in the Analysis panel, move the diet variable to the Analysis box, and select the Tukey correction. This method applies the strict criteria necessary to prevent the family-wise error we discussed earlier. You should also check the box to flag significant comparisons. To make these results easier to communicate, go to Descriptive Plots and map the diet variable to the horizontal axis, then enable arrow bars. This Tukey table identifies our specific winners. While there is no significant difference between weight loss on diets A and B, Diet C is significantly more effective than both of them, with p-values below 0.001. This post hoc testing allows us to answer the core research question with precision, ensuring our final conclusions are mathematically sound. The final step is translating these software tables into a formal paragraph for your research report. We begin with the Omnibus results. We report the F statistic, the degrees of freedom, the p-value, and the effect size to establish that the diet type had a significant impact on weight loss. Then we use the Tukey p-values to write the specific findings. We report that Diet C resulted in significantly greater weight loss than A or B, while explicitly noting that diets A and B were statistically equivalent. By following this process, you've turned a raw spreadsheet into a defensible, actionable scientific conclusion.